Okay, welcome to the second video lecture for ECE 203. Again, I want to remind everyone that these video lectures are really meant to just cover essentially the same material that we saw in class, so there's no need to watch these unless you missed something in lecture or if you just want to review. So last time, one of the first things we did was we defined the three terms in the title of the class, which are signals, information, and computing. I want to spend just a little bit of time talking about specific signals and examples of signals that we're all very familiar with. So if you recall, the definition of a signal is a measurable quantity that may vary with time or space. So a number of time-varying signals that we're very familiar with. Of course, acoustics. So just my voice is a time-varying signal. It's a pressure wave that varies as a function of time. Okay. Another one common in electrical engineering is, of course, an electromagnetic wave. So, for example, a radio transmission on your favorite FM radio station. Okay. There's other electromagnetic waves used for communications that are signals. So a cell phone transmission, something like sunlight, right? That's also a time-varying signal. If you look at the intensity of sunlight at a particular point as a function of time, of course that varies a lot from day to night. Also, this video is, of course, a time-varying signal. When we think of spatially varying signals, we might think of things like an image or light. And now, I guess before I keep going with the list, I just want to point out that a lot of these signals we're talking about are both time-varying and spatially varying. Okay, so video, which I just happen to put in the time-varying column, is also spatially varying. Right? If you look at different pixels in a video screen at a particular time, if you pause the video, right, it's those pixels, the value of that pixel changes as a function of location. Okay, so there's other signals, right, related to weather. For example, snowfall totals across the state of Wisconsin for a particular winter storm. Maybe traffic patterns, temperatures across some geographical area. And then also, what we talked about in MRI, and that was maybe the density of hydrogen atoms inside a person. And that's a signal that varies as a function of space. So the next key component that I want to talk about is systems. Systems, the way we'll define them, take one or more signals as an input and then simply output another signal. Familiar with would be a digital camera, okay? And so the signal that's input into a digital camera is actually just light. So the input here is just a light signal. And the output of a digital camera is just going to be maybe a digital image, right? So the output will just write an image. If we look at a cell phone as a system, an input could be, there's a lot of inputs to cell phones, right? One might be if you're making a phone call, the input would be speech. Of course, the output here from your cell phone, the output is an electromagnetic wave, and that's transmit to a base station. So the signal is the cell phone transmission. The output signal, is a cell phone transmission. The input is your voice, and the system converts your voice to that electromagnetic signal, that cell phone transmission. Okay. And that cell phone transmission is, of course, in an electromagnetic wave, very particular electromagnetic wave. So the next thing I want to talk about is how we represent signals and systems mathematically. So on the left, I've drawn a simple plot of function x of t, which is a function of time. So on the x-axis we have time, and on the y-axis we'd have x. So let me just note that here. So time would be increasing here, and here's x of t represented on this vertical axis. Okay. So a signal is represented, a time varying signal is represented as a function of time. We also have spatially varying signals. An example of that is an image. So the image that's shown on the right, which is just a simple drawing of a pine tree, is a spatially varying signal. So as the spatial location is now represented by this m and n, and the function is represented by x of m and n. So the inputs are two spatial locations, so that would be the location. This point would have some value, and that would be some value of m and n. You can just think of those as the spatial location in 2 dimensions, and x of m and n is the value of the image, the value of the pixel at that point. Signals are represented by this kind of mathematical function, right? Both time varying and spatially varying signals. And systems which act upon signals and output other signals can be represented as mathematical transformations of signals. Okay? So that's what I'm trying to indicate with this block diagram here. Here we have some input x of t, so a time varying signal. The system does something to that signal, and the output is then y of t. So maybe a simple example of that would be a system that squares the input. The output, we could just write that, would just be y of t equals x of t squared. So that's one type of system. We're going to look at a lot of different types of systems as we progress in the course. So the next thing I want to talk about is sinusoids. Sinusoids are going to be the fundamental building block for signals that we look at in this class. And there's a number of reasons why sinusoids are so important. Okay? That's what I have drawn in this top picture here. I'm going to, again, call this signal, say, x of t. And maybe just say x of t equals cosine of t, for example. So I can look at just one cycle or one period of the sinusoid. I'm going to just highlight that in blue. And a key property of sinusoids is that they repeat. Okay? So they're what we call periodic. Well, the reason these are so important, one reason is music. So music is actually made up of different sinusoids. So you think of different notes related to sinusoids. And so music itself is made up of sinusoids. Right? And there's, of course, other reasons. One, communication signals are also made up of sinusoids, slightly perturbed sinusoids. An example of that would be, you think of your favorite radio station, maybe it's Z104. That's not my favorite radio station, but I bet a lot of people in the class like that. And that's 104.1 megahertz. Okay? So what does that mean? That means it's a sinusoid, right? Sinusoidal signal that has the number of periods, these things I've drawn in blue, that repeats 104.1 million times per second. There's a reason why communication signals are made up of sinusoids, and that's because of fundamental physics. So we saw with the tuning fork example, there was a simple physical structure that made a very pure sinusoid. Okay? So the fundamental reasons behind physics are, examples of that are a tuning fork, right? And then more relevant to electrical engineering, there are things called crystal oscillators. And a crystal oscillator just creates a sinusoidal voltage at a very precise frequency. Okay? And the reason it creates a sinusoid is based on the physics of this device, and it's a natural signal. You can use that for a lot of things, including communications. Okay? Crystal oscillators. Then yet another reason is for signal representation. And we'll learn in this class that we can actually represent any signal with a sum of different sinusoids. So even if the signal doesn't look anything like a sinusoid, we can still represent it as a sinusoid. So any signal. So the last reason I want to mention that we look at sinusoids is for system response. Okay? So if we want to mathematically model what a system does to a signal, if it's a particular type of signal, which we'll learn about later in the class, then it can be entirely characterized by how sinusoids respond to that system. Okay, so I'll just write here, can be characterized by effect on sinusoids. So how do we represent a sinusoidal signal mathematically? Well, I've written just x of t here. Okay, and we say x of t again is a time-varying signal that t is meant to indicate. X is a function of time, so x varies with time. And we've written a particular equation just to the left of that, and that's a times cosine of omega naught t plus phi, right? So here the a represents the amplitude of the sinusoid. Omega naught, or equivalently f naught, represent the frequency. In particular, those two are related, omega naught and f naught are related through the equation you see right here. Right? And there is a distinction between the two of them. Omega naught is often referred to as the angular or radian frequency, and the units of that are radians per second. So if you think of a circle, a unit circle, there's 2 pi radians in a circle. And if you think of traveling around that circle as one cycle, then if you travel a certain number of radians, a certain amount of time, think of radians per second. Okay? So it's a very simple relationship with f naught, and f naught is just the frequency. And the frequency is in units of cycles per second. Okay? So you see f naught show up in this equivalent expression here. Okay? So omega naught is just equal to 2 pi times f naught. Last thing that we'll see in here is phi, and that's just the phase of the signal. Okay? So I have just a little sinusoidal wave function drawn down here. Okay? And just one period of the sinusoid. So there's a couple of things to note. The amount of time it takes for this sinusoidal signal to go through one period is equal to t naught seconds, okay? And that's 1 over the frequency. Equivalently, that's equal to 2 pi divided by omega naught, and that unit is in time. Okay, so the period just tells us the amount of time it takes for the sinusoid to start repeating itself. The last thing I want to reiterate is the units of omega naught and f naught. So again, omega naught is the radial frequency, and the units of that are radians per second. If you think about F naught, in a lot of ways that's more natural. Okay, that's the number of cycles. So this drawing is one cycle. So F naught tells you the number of cycles that happen in one second. And the unit of this is often referred to as hertz, which will just abbreviate HZ, after a guy named Henry Hertz. Okay? But the unit is really just cycles per second, or number of cycles in 1 second. So that's the basic structure of sinusoids. Let's look at a particular example of how we might begin to plot a sinusoidal signal. So here x of t, right, time varying signal, is just equal to 10 times the cosine of 2 pi times 100 times t. So the amplitude is just 10, right? So we just got that from there. Okay. The frequency in hertz, or in cycles per second, is 100. Okay? And that's just this part here. It's multiplied by 2 pi times t. So of course we could just write the angular frequency, omega naught, would just be 200 times pi, right? And for now we'll let the phase be equal to 0. So how will we begin to plot this? Well, one thing we could do is just start evaluating this sinusoidal waveform at different times. So we could say, let's evaluate first x of t at t equals 0. So what is the value of the function at x of 0? So this is times 0. Well, that's just equal to, right, of course, 10 times the cosine of 2 pi times 100 hertz, right, times 0. Okay. So this is, right, just 10 times cosine of 0. And if you remember back to trig, cosine of 0 is just what? It's just 1, right? So this just equals 10. And that's exactly what we see plotted here, right? At x of 0, we see the value 10 right there. Right? So there's one point we evaluated at. And then we could continue in this way, right? And say, now what's the value of, I just noticed on this axis, this time should be in milliseconds. Okay. So we come down here and I'll just say, what's the value of x at, I have these picked out already, but say x at 0.005. So that's 5 milliseconds, right? Well, again, do the same thing. That's 10 times the cosine of 2 pi times 100 times 0.005. Okay. So 100 times 0.005, that should give me 1/2. Right? You just write that here. That's going to be equal to 10 times the cosine of pi, right? So this guy equals 1/2. The 2's cancel, and we're just left with pi. So that equals, right, if you remember, -1. All right. So again, now we have another value. Right? We just say at t equals 5 milliseconds, the value should be minus 10. And sure enough, it is. All right, let's do one more value, so I think you guys get the idea. But let's just look at x at time 0.0025. We do the same thing. It'd be 10 times the cosine of 2 pi times 100 times 0.0025. Right? And that's just, if you multiply that out, that's just going to be 10 times the cosine of pi over 2. And that's, again, remembering your trig identities, that equals 0. Okay, so I want to remind everybody how to see these values of the cosine. So if I were to draw two axes in a circle, okay, and just basic trig, so here is the angle, we'll call that theta. If you remember, so we'll say that the length of that circle, or the radius of that circle, if it's equal to 1, we have the cosine, we'll call this x, and this y. The cosine of theta equals x. And also the sine of theta, that equals y. Okay. So the values here, this axis, this y-axis, this is pi over 2. That's pi over 2 radians. This is pi radians. And this is 3 pi over 2 radians. So we can figure out from that unit circle, just to remind everybody the basic trig, how to remember what the values of cosine theta and sine theta are. All right, so we saw the last value we saw, right, is at 2.5 milliseconds. So we can come back up to the plot and we can just say, yep, sure enough, at 2.5 milliseconds, the value of that signal, of that x of t, is just identically equal to 0. Let's do one more example of plotting a sinusoid. So you'll notice this example looks almost the same as the last one that we just saw, except the difference is the frequency now is 200 hertz instead of 100 hertz. So we could proceed in the same way, just evaluating the sinusoid at different times. Or we could just look at this and say, well, we know that the amplitude should be 10, right? So the maximum value that this is going to take will, of course, be the value 10. So we could just, draw that on the axis as a starting point. So say this is plus 10, and then put minus 10 down here. We could evaluate this at time 0 again, just as before, and we'd see that the value of cosine of 2 pi times 200 times 0 is indeed 1. That gets multiplied by 10. So at time 0 we know the value is 10, just like before. The difference in what we're going to do now is we can just look at, instead of evaluating this at more points, we can say, since we know the maximum happens at time 0, we can then just look at the period of the sinusoid and plot it just using that information. So since f naught is equal to 200, we know that that will give us a period of t naught, which equals 1 over 200 seconds. So we know that every 1 over 200 seconds, the sinusoid should make a full period. Okay. So 1 over 200 seconds, right, that should just equal 5 milliseconds, which of course is 0.005 seconds. So now I would just come down to this, the plot, and I would say, well, since I know it has to repeat every 5 milliseconds, we know the value at 0, that should be right there, somewhere up there. Just make a big mark. And then I also know it has to go through 1 full cycle, and then by 5 milliseconds it also needs to be back up again at the value of 10 because it made a full cycle. So, and I know what a period of a cycle of a sinusoid looks like, right? You can just say, draw that in green. I know that should come down and hit minus 10 at the value of 2.5 milliseconds. So, and I would continue in this way in both directions, and we'd have a rough plot of what this sinusoid looks like. So here we really just saw the effect of increasing the frequency. If you recall on the last screen, the frequency was f naught equals 100 hertz as opposed to f naught equals 200 hertz. So increasing this frequency made the sine wave repeat faster, right? And it looks just like it oscillates twice as fast, and that's actually precisely what happens. I want to talk very briefly about sampling, just to kind of get everybody a first glimpse of how this might work. Of course, when we're using MATLAB and digital computers to process and do computations on signals, we can't, this doesn't happen with continuous signals like we're drawing. We actually just need to sample the signals, and then we store those numbers as a vector in the computer. If we were to store this the same original cosine wave that we saw 2 slides ago in the computer, the way that would happen is we'd first have to define a sampling frequency. Okay? And a sampling frequency, that just means the period or the repetition rate at which we're going to sample this sinusoid. And that's usually denoted T sub s. This is the sampling period. And all that indicates is the amount of time between when I'm going to take samples of the sinusoid. So if I set T sub s equals 2.5 milliseconds, and then I sample the sinusoid above, that would look something like this. Let's say I start at time 0. I would take one sample here, okay, and then I would take another sample. So we'll draw that kind of as a stem. I draw that as, take another sample at 2.5 milliseconds, then another one at 5, another one at 0, another one at 10, and so on. Right, so the values that I'd actually have stored in the computer, now I could just write that as a list of numbers. So at time 0, the value would be 10, right? And then at time 2.5 milliseconds, the value would be 0. And then at time 5, it would be minus 10. And again, at 7.5, it would be 0. 10 seconds value would actually be 10, and so on. Okay, so that's how sampling of a sinusoid works. Now, just to show you guys in a little more detail, I could increase that sampling rate, right, by decreasing the sampling period. So let's just say now instead of 2.5 milliseconds, I just decide to set the sampling rate at 1.25 milliseconds. Then of course, when I come back up to this plot, now we're going to be sampling the sinusoid in between, right? In between these points as well as at these original points that I drew. So you can see when you increase the sampling rate, it actually becomes easier to reconstruct or represent the sinusoid. Remember now, when this is stored in the computer, the green line won't actually be stored, right? You're just storing these values at these blue points. So the faster the sampling rate, or the smaller the sampling period, so the more frequently we sample, the more we're able to represent rapid changes in this signal. All right, so that's just a quick introduction to sampling. The last thing I want to go through is a quick, simple MATLAB example to get you guys started on thinking about how we can plot sinusoids in MATLAB. So it's about 11 lines of code, and I'll just walk through this and explain what this does. So the first two lines, the clear and close all just means close all the open figures. So all the plots that MATLAB has already has open get closed. So close figures. The clear statement is a little more important, and that just means clear all the variables from memory. So that means if you stored any numbers associated with a variable, that gets cleared. Right? So say you had entered a equals 7, that would be erased from memory, and you could no longer refer to a without seeing an error saying that the variable doesn't exist. So that clears all variables. All right, and now what the actual code does. So the first line is just defining T sub s to have the value 0.001, or TS to have the value 0.001. And intuitively that's going to represent the sampling period at which we're going to sample the sinusoid. Okay? So that's just associating with TS the value 0.001. Really simple. Right? And you can see the semicolon at the end of the line. That just tells MATLAB to not print that output to the screen when the code runs. All right, then the next line is Tn. Okay? Tn is going to be a vector, and what this code is telling MATLAB to do is saying it's start at minus 0.02 and create a vector that increments by the value Ts, which Ts is 0.001, and do that all the way out to the value 0.08. So Tn, the variable Tn, is just a list of numbers. It's a vector, and it starts at minus 0.02, and then the next value would be minus 0.019, if I did that right. So it's just increasing by the value of 0.001. So the next value then would be minus 0.018, and so on. You'd eventually hit 0, right? And then you'd have 0.001, and then a bunch more dots, all the way out to 0.08. So that colon notation, again, this line right here, this line right here tells MATLAB to start at the value minus 0.02, create a vector that increments by 0.001 and goes all the way to 0.08. All right, the next line just tells MATLAB then to create another vector called yn, okay? And yn is just going to have the values. It's going to be another vector. It's going to have the values exactly 20, times cosine 2 pi times 50 times, now this vector here gets put in there. So it's going to evaluate the cosine at all the values of Tn. So Tn and Yn are now vectors, lists of numbers that are the same length. Alright, so we're ready to plot now. We have two vectors of the same length. We have Tn and Yn, just two lists of numbers. So here's that exact same code that we just analyzed and went through. And now if I just have this in a script in MATLAB, and if I just click Run, I see a plot of this sine wave. Okay, and the value that it should start at is this value, the smallest value of the vector Tn, which is minus 0.02, and then it goes all the way out to 0.08, and it's going to increment by a value of Ts. Okay, and you see these. You can actually zoom in here. You see the red points are that the stem plots are where we're actually evaluating the sinusoid. And of course I can increase, so let's say I want to increase the sampling or decrease the sampling value. I can decrease the sampling period to 0.0005, so half a millisecond. And the effect that that has is now I've sampled twice as frequently. You see twice as many samples.